So, good afternoon. My name is Eduard Montellà. Today I'll talk about dense granular flow around a cylindrical object. And this work was possible with the help of Julian, Bruno Saga, Cyril Bonamy, and Tom Su. So before I dip into the details, I'd like to say a few words on the motivation of the project, and that's particle size segregation. When we're referring to particle size segregation, we're referring to the big particles that go up to the surface, while the small particles migrate to the bottom in shallow granular flows. A classical example is found in mountain rivers, where we find like big rocks or gravel on the surface, while the fine material like sand stays at the bottom. Another classical example we can find it in landslides or debris flow, and in this case, when the big material goes up to the surface, because the top surface is going faster than the bottom, the large particles, the rocks or the debris, are brought up to the front, as you can see in this image, and that increases the potential danger of these granular flows. Apart from these geophysical flows, the particle size segregation is also a major concern in industrial application, especially in the pharmaceutical and the food industry, where the particulate material is usually stored in silos or big tanks, and the problem comes when we want to take the material out, because then we shear the granular material and we enhance the particle size segregation, which is very inconvenient because we usually want uniform distributed material. So for this reason, there are many people that have already studied the particle segregation phenomenon and try to figure out what is the mechanism behind it. Here there's an example of an experiment. It's an oscillatory seal shear. So there are two plates like this. They fill it with granular medium and they rotate it like this continuously. And they observe that when you consider a big intruder inside the granular medium, it goes up after a while. Here there's a video that we cannot play, unfortunately, because it's a PDF. But what they did in this experiment is they placed the orange particles that were larger in this Couette flow, and they were initially placed at the bottom, while the small particles, the black ones, were placed on top. And when they shear it, all the big particles went up. So in most of the literature, they come up with two main mechanisms that were initially proposed by Savage in the late 80s. The first one, it's the percolation or kinetic sieve. In this case, when we have a mixture with different particle size, and you agitate the mixture or you shear it, what's happening is that the small particles fall down into the gaps between the big particles. So by the end, after a while, we end up with a significant amount of particles at the bottom, as you can see here. And when this happens, it starts the second mechanism, which comes from an imbalance of contact forces. So here we observe that we have a significant amount of particles that are in contact with the big one, while on the top there's less particles in contact with the big one, and that creates a force imbalance that pushes the big particles out. This phenomenon it takes much longer than the previous one, and it's still not fully understood. Well, so all boils down to what is the lift force, on a big particle or a big object, and is it big enough to overcome gravity or not? With that, we can write down two objectives for this project. First one is, can we reproduce lift force on a symmetrical object, such as a sphere or a cylinder, using an Eulerian approach? And if we can do it, if we're successful, can we make the object move using a dynamic mesh, for instance? So in this context, we're going to reproduce the numerical simulations of ER, and we are going to use these numerical simulations as a benchmark to validate our numerical approach. So what Eduard did by means of the discrete element method is they place a cylinder in a granular material. So this tank is full of particles, and then they drag all the particles horizontally with a constant velocity, and they evaluate the forces exerted on the cylinder and the pressure and the velocity field around the obstacle. As a first step, they turn off gravity, and what they observe is that that's the direction of the flow. There's a high pressure area upstream and low pressure area downstream. Nothing surprising here. That's the origin of the drag force. And if you can see that with respect to the horizontal, the field is completely symmetrical. But when we turn on gravity, then the things get a bit weirder, and what's happening is the high pressure region is tilted slightly downwards, while the low pressure region is shifted upwards, and that creates a non-symmetrical field that eventually pushes the cylinder up. This is a bit unusual if you come from the fluid mechanics community, because we need a non-symmetrical object like an airfoil or an inclined plane to generate lift, but things work a bit different in granular materials. This non-symmetrical behavior is also observed in the velocity field. So maybe you cannot see it from in the back, but here when there's gravity, what they observe is that the velocities are much higher above the object rather than below. And what Eduard claimed is that the origin of the lift force on a cylinder or symmetrical object, it comes from the gravitational pressure gradient, and the frictional rheology has a very important role distorting the flow pattern. When I'm talking about frictional rheology, what I mean is that the stresses are proportional to the pressure, unlike fluid mechanics, where we usually assume that the stresses are proportional to the velocity gradient. So let's put our hands on the mathematical model. So to reproduce Eduard numerical simulations, we're going to use SetFOAM, which is an extension of the two-phase Euler foam modified to handle sediment transport applications. So we are solving the mass and momentum equation for the solid and the fluid phase. Here I'm not going into the details. I will briefly mention the different contributions in the momentum conservation equation for the solid phase. So there's the gravity of the particles, the weight of the particles, the buoyancy, the drag force that enables the coupling between the solid and the fluid phase, the solid stresses, and finally the fluid pressure. And I'd like to extend myself a bit more on the solid stresses. So here in this slide, don't be overwhelmed by the number of equations here. They are not really important for the scope of this presentation. But what I want to convey is that we can adopt different closure forms or different rheologies to model the solid stresses. So let's start with the solid pressure that we usually divide in two contributions: the binary collisions. So when we shear a granular material, there are some particles that collide between each other, and especially in a dilute regime, so when the concentration is low. And then we have the contact pressure, that it comes from the enduring contacts between particles, and it's dominant in the dense region. So because we're dealing with dense granular flow, this one is the one that is going to be much more dominant. And what we can see is that regardless the rheology, so the solid pressure is basically a function of the concentration and the elastic modulus. And if we now take a look on the shear stress, the simplest approach is the Coulomb approach. It's basically that shear stresses are proportional to the pressure by a factor that is the frictional coefficient, and the friction coefficient is set as a constant. But in dense granular flows, instead of considering the friction coefficient as a constant, it is a unique function of the inertial number that in turn depends on the shear rate and the solid pressure. And the important thing about the mu rheology is that it's a local rheology. That means that the stresses depend on the local shear rate, and this is the most suitable for dense granular flows. So that's the one we're going to use in most of the presentation. And finally, we've got the kinetic theory, and in this case, the friction coefficient, it adopts a very long expression where we have this theta that's called the granular temperature, and it includes the fluctuation of the velocity. So by that we're embedding some non-local effects. So that's the reason we call it a non-local rheology, and this is more suited for dilute flows. So here we have the boundary conditions that we are imposing to reproduce VR numerical simulations. So cyclic boundary conditions, inlet and outlet, so slip condition top and bottom, and zero gradient for the concentration. And we also impose a constant velocity through a pressure gradient, and that's by means of the FB option. And here there's a summary of the physical and geometrical parameters that we use to reproduce VR numerical simulations. So finally, we've got some results using ZFOAM. And here's the comparison with the VR numerical simulations using DN. So we can observe that we managed to reproduce this non-symmetrical behavior in the pressure field. So the high pressure region is slightly tilted downwards, and the low pressure region is located a bit upwards. That means that we reproduce this non-symmetrical behavior that eventually generates lift on the object. And concerning the shear stress, what we observe is that the maximum values are around 30 degrees here on the upstream phase, in agreement with VR numerical simulations. And if we now take a look on the velocity fields, what we get is, again, a good match with VR numerical simulations because velocities are much higher above the object. In the bottom two maps, what we have is the vertical velocity. So you see that here the velocities are they have a larger magnitude. That means that when the particles are approaching the obstacle, they tend to pass over the object instead of going beneath. Also in agreement with numerical simulations from VR. So up to this point, we were pretty happy. The results seem great qualitatively, but we got less satisfactory results when we went more into the details and analyzed the stresses around the cylinder. So here we have the normal stresses, okay, at different locations around the object, and here we have the tangent stresses. So first thing we can take a look on is at the most downstream point. In this case, what we observe is that there are no stresses at all. That means that the particles are detaching from the cylinder, so there's no real contact between the particles, the grains, and the object. And if we take a look on the peak is for a VR numerical simulation, it's around 20 degrees, so slightly tilted downwards. But for us, there's a certain shift, but it's very, very low. So we didn't manage to reproduce the same amount of non-symmetrical behavior. So there's some non-symmetrical behavior, but not enough. The good news is the drag force that can be seen as the area beneath the curve are pretty similar with VR, so that's good. And finally, for the tangent stresses, they follow a very similar path. But again, we're missing this non-symmetrical behavior. Our curve is like almost symmetrical, and for them it's slightly shifted. So we're missing that. In fact, at this point we were wondering, okay, what's missing in our model? And we performed some sensitivity analysis, and the only variable or the only ingredient that could reproduce this non-symmetrical behavior was changing the rheology. And so we tested the kinetic theory. If you remember, I told you that this is not really suited for dense granular flow. It's more for dilute flows, but it was worth trying it. And what we get is that we managed to reproduce the peak at the peak position, I mean. but the curve gets a bit narrower, which is bad because then we don't reproduce the same amount of drag force. So here we can see that the distribution of the normal stresses are much better. It's clearly shifted downwards, while before it's very difficult to see it from your perspective, but because the maximum point is around 2 degrees, which is pretty bad. It should be around 20 degrees. So here at this point we're wondering, okay, fine. It seems like what is missing is the rheology. So in the kinetic theory, there's the non-local effects, and that's what's probably missing. And we are now performing some DM simulations ourselves. Well, I can play the video. That's okay. Yeah.
You can minimize the video.
So we perform some DM simulations, so we can evaluate more precisely what's going on around the object and try to determine try to evaluate some microstructure data around the object. So that means that apart from the classical fields that I show you over and over, the pressure field and the velocity field, I can have access to more local data, such as the shear rate around the object or the coordination number that stands for the number of contacts of a particle with its neighbors. And with that, we hopefully, because this is still an ongoing work, we can get more information and build a new non-local rheology and implement it in SetFOAM. So talking about ongoing work or unfinished work, now at this point we were wondering, okay, can we make the object move and simulate the granular flow around the cylinder and try to lift the object? So we implemented the 6 degree of freedom library in SetFOAM. So we had to modify the code to include the forces of the sediment exerted on the object. And here, as a proof of concept, I perform well, I will consider 2 cylinders, this one and the one that I'll show you later, that have the same density, and the density of the cylinder is slightly lower than the mixture. So when we place them like immersed in the granular medium, the buoyancy is higher than the gravitational forces, and it goes up. And if we did the opposite, then it goes down, and eventually it goes up again until we reach the new equilibrium. So the preliminary studies seem promising. There's always a but. And when we perform that in the granular flow, so the cylinder, and try to simulate the lift, the results were pretty bad. I'm not even showing them. And here, what I want to convey with this slide is what we learned so far, because our group is quite new in terms of dynamic meshes or dynamic objects. So we have implemented overset and the morphing mesh, and what it seems is that the morphing mesh approach is more suited for our cases, especially when the object is touching the interface, because you get less numerical noise. And also, we were testing the use of mules, because we're interested of not using mules. And that's because most of our numerical applications were interested in the resuspension of the sediments. And using mules, we compress the interface, and it's more stable. But as you can see here, and when we don't use it, there's a lot of numerical noise. But well, at this point, we were wondering if anyone has any idea about what's going on when we consider we don't consider mules, and if any of you have ever tried to implement interdynamic foam without mules, I would be curious about that. So that brings us to the end of the presentation. So 3 takeaway messages. First one is that with SetFOAM, we're able to reproduce qualitatively good results in terms of pressure field and velocity field for granular flow around a cylinder, but something is missing, probably the non-local effects. And we are studying them using DEM. And finally, we've learned that the morphing mesh is probably more appropriate for our cases, and we are still investigating the use of the Niels limiter. That would be all. Thanks.
All right. So, thank you for the presentation. So we see if we have any questions from the audience, and I request you to repeat the questions so that.
Yep.
Do we have any questions? You can ask it and please repeat the questions for the system.
When you said this is a mesh, demonstrate mass props, what kind of magnitude or mass props
It's well, sorry, I have to repeat. So they were asking if what is the percentage of the mass loss when I'm using overset. And thing is, the moment in which the obstacle is like in contact with the interface, I don't know exactly if it's the interpolation or what is causing that, but it's kind of the cylinder is sucking the mass, and it's really like 50% of the mass, so it's something that it's pretty bad.
Do we have any more questions?
What is the aim of using your SetFOAM and not the approach? What the aim?
Well, what we want is to implement it in a larger scale, because DEM clearly cannot do that, and with that we want to reproduce like I'll rephrase. So one of the fundings of the projects is a organization in the States in which they are interested in the re-emergence of the mines and in some beach near the coast, and that requires a lot of large-scale simulation, and that cannot be done with DEM. So we're just using DEM as a benchmark, and once we can reproduce similar results, then we can do it with SetFOAM in a larger application.
All right. So I'll just check if there is any question online. Can you please? Is it this?
Any comment related to flamelet model? But I don't know it.
Probably it's related to some previous session or this. Yeah, it's related to previous.
Yeah.
Questions in Q&A section.
Right. Okay. So I think you have the mic.
Oh, they just vanish.
So basically, if you click on the question, it will show you who posted the question. So there is the gentleman
I
here.
think these questions.
No,
This is from the previous session.
Maybe the last one.
Yeah, maybe the last one.
Okay.
Nice presentation. I'm just wondering how you implemented the effect of gravity into OpenFOAM, as many solvers don't account for this effect. In addition, how was the buoyancy implemented? So no, it's basically it's here. We just added in the conservation equation for the momentum conservation equation for the solid phase. So we're solving the weight, so part of the gravity, and then the buoyancy, and finally what we are finally solving is just the excess of pore pressure instead of solving pressure as in pimple form. But I think there are several solvers that already do that. I mean, we're not the first one.
So for the interest of time, let's thank the speaker and for the presentation, and we'll go ahead.
Thanks. Oh.
Basically, now I invite Ms. Justyna to give the presentation on the benchmark simulation of the flow-induced vibration for nuclear application. And the stage is yours. Please continue.
Thank you for the introduction. So, as already said, my PhD project was typically devoted for nuclear applications. The project was sponsored by the EDF R&D UK Centre and is supervised by Dr. Andrea Ciancolini and Professor Hector Iacovides. So, a couple of words about the introduction. Why I'm actually analyzing the flow-induced vibration. It's the problem for two major nuclear reactor components, a heat exchanger and the fuel assembly. And these vibrations, the excessive vibration from the flow, induce what's called the grid-to-rod fretting. This phenomenon leads to a component failure and is typically numerically solved with this FSI simulations, analyzed with the FSI simulations. So in order to present the problem, I depicted the entire fuel assembly, which consists of hundreds of fuel rods arranged in the square lattice, and these are put in place with the component called the spacer grid. It has a two function. It holds the fuel rod in space, but also enhances the flow mixing by inducing turbulent field. And this is an example of a fretting wear, which I was talking about, experienced by EDF. And these fretting marks were found at any axial location of the fuel rod, but the deeper marks were found at the bottom. And the amplitude of vibration is very little, almost negligible, because the flow is mainly actually directed with the fuel rod. So at the beginning of my studies, I started to analyze the sources of VIV, and the first which I identified, which was actually obvious one, is the turbulent buffeting. So the excessive forces from the turbulent boundary layer, which are excessive to the what was designed for. But also, we need to deal with the fluid coupling. So the one movement of the one rod can induce the movement of the neighboring rods. If for a simple experiment, if we put 4 rods in a quiescent fluid, if we move one, they will reply with the same frequency through fluid coupling. Therefore, I had to choose the two-way FSI implicit, and I picked OpenFOAM solver, new one, solids for foam. And in Manchester, we have a capability to test this problem experimentally. We have a cantilever beam with 2 end shapes subjected to the axial flow, turbulent flow. And one camera tracks the displacement and the second camera tracks the flow field. So here is the example of the flow field captured with the VIV. And this is a displacement track denoised. And as you can notice, the displacement is really marginal. But if we increase the velocity, the blunt end experience higher amplitude of vibration than the streamline end. To a certain critical velocity. So to a certain critical velocity, there is no difference between the end shapes. If we increase the velocity, then the blunt end experience higher amplitude. Having that, I also analyzed the other numerical studies with the same, approaching the same problem, and most of the researchers analyze only the frequency and damping ratio of the beam, and also the induced vibration appear to be damped, whereas in experiment we can see that there is a constant excitation of the beam. And so far, only the LES simulation is believed to reproduce the turbulent flow field and the pressure fluctuation, so that it excites the structure constantly. So here is the methodology I've used in my studies. I wanted to create a benchmark simulation to simulate turbulence-induced vibration on a flexible structure, and basically to reproduce the same experiment as we have in Manchester. And I've achieved that with 3 fully validated projects. One was the validation of the FSI solver. Then I tested the unsteady runs models to simulate force fluctuations. And finally, at the final stage, I've managed to have a simulation with the beam subjected to the turbulent flow. So starting a couple of words about the validation of the FSI solver, I've used the famous RON benchmark where elastic beam is subjected to Born-Kármán vortices behind the rigid cylinder. And I've used Laplacian smoothing with linear diffusion coefficients, and I had to refine the mesh quite a lot to reach to the benchmark, but I know for a fact that my final goal is to simulate low amplitude of vibration. And just a couple of words about the Laplacian smoothing, but there was already yesterday, there was a dynamic mesh training session, so I won't go much to the details, but linear distance base is very good for small deformation. For large deformation, I would consider radial basis function, which is implemented in solids for foam. And also my approach in FSI was to first test the fluid side, then test the solid side, and then combine these settings together in the final FSI simulation. So starting from the fluid side, I tested the unsteady runs models. I wanted to avoid using LES. And in runs modeling, we time average Navier-Stokes equation, and we have a component called the Reynolds stresses, which we approximate with 2 extra PDEs, either K omega, K epsilon, or K omega SST, and this is a typical industrial approach. Also, I wanted to test Reynolds stress models, which actually model Reynolds stresses with 6 extra partial differential equations. And this is mostly applied in jet impinging or strong streamline curvature applications. So to analyze this turbulence model, I've selected a separate rigid case where I have a flow field over a forward facing step, and there is a series of pressure transducing along this beam. And what was found that pressure, the highest amplitude of pressure, it's found at the reattachment length. So I created a very simple test with the 2D mesh with the wall functions and orthogonal mesh. And what I've discovered that the third order scheme reproduced the pressure fluctuations. The first order and second order really dump the pressure signal after some time. And here is the result of the flow field and pressure against eddy viscosity model against the Reynolds stress model. So immediately we can see that we reproduce the large eddies which induce vibration. And actually further studies showed that the energy content of these pressure fluctuations reproduced with Reynolds stress model is the same as in the experiment, means that I reproduce the pressure fluctuations which would be responsible for excessive vibration, and it's sufficient for further studies. So now I move towards the actual benchmark against our experiments in MACE. So this is a design computational domain of the experiment. Simple single beam, cantilever beam subjected to the flow field. And I apply the Reynolds stress models as in the previous section. So I don't only concentrate now on this Reynolds stress model. And interestingly, I just want to show the benefit of our experiment. We also have, we track the velocity profile so you can validate your flow field. And I reach 1 second of the flow field with 2 hours simulation on 16 processors. Very amazing. For the same configuration, LES would take 4.5 days or 3,000 processors. But actually that poses a question, what if I started from LES? How many processors, how should I decompose the solid side when using LES with using a solids for foam? That's my question to the community. And also what I've encountered, one problem I've encountered during this simulation approach, I wanted to now validate the cantilever beam subjected to the peak force and analyze free vibration of the beam. And I've chosen the properties matching that match to the experiment. And in order to get freely vibrating reply without damping, I have to use a very small timestamp. But I wanted to have a simulation. I wanted to simulate, let's say, 3 seconds in a week. And I had to limit the number of outer loops. And I experienced a numerical damping. But in the actual experiment, two-way FSI, the beam will be subjected to constant excitation. So I don't really bother about the damping. However, that's what you should consider when you simulate with a segregated approach, that it really takes a lot of time to simulate the movement of the beam without experiencing a numerical damping. So at the final stage, I combined the flow field from the first simulation and then the cantilever. And I've actually get pretty nice results. Two-way FSI, I can visualize the movement of the beam. And I didn't have to use large residual, a very small residual, because I knew that the amplitude of vibration will be little. And interestingly, I reproduced nicely the amplitude of vibration, which is not really happening often, that we reproduce amplitude at the same ranges as in the experiment. And natural frequency of vibration matches nicely the experiment. And also the movement of the beam was triggered by the flow itself. And it's, but 1 second of the simulation takes around 4.5 days on 32 cores. And it's mostly, the time is mostly dominated by the segregated approach on the solid side. And just to show the comparison between eddy viscosity model, so I barely reproduced the amplitude of vibration, only the small wave, which actually has the same natural frequency as in the experiment, of course, with a higher error, but the amplitude is negligible. So my conclusion of my old PhD was that eddy viscosity models are insufficient for this application, and only Reynolds stress models, at minimum at least, are capable to simulate the amplitude and frequency of flow-induced vibrations. And more importantly, I have reasonable CPU time as opposed to LES. And this benchmark can be used then for further investigations like two beams in a confined fluid, instrumentation, or entire fluid assembly can be modeled. And of course, this approach can be adopted to other industries like automotive industry, where we're dealing with the pressure fluctuations in an exhaust system, or aeroelasticity. But what about the LES simulation and the large fluid domain as compared to, so if we have a large fluid domain and a small solid domain, whether we can still use LES? That's my first question. And second of all, whether I can use solids for foam. And if from the community, if you experience the same problem with the solid side, computational time, and if there are any improvements on that. So that's all from me. Here are the references I've used, and feel free to ask questions.
Thanks, Justyna. So I'll just go to the audience if there are any questions to Justyna. If not, I think C asked. Okay, Philip asked. Thank you.
Hi, Justyna. Thanks so
Yeah.
much for really nice talk. Yeah, just on the last point, the computational inefficiency of the segregated solver, I think these block coupled approaches is one way to solve that for these styles of problems, particularly for cantilevers where you can have orders of magnitude speed up. The only thing is they're less developed in solves for fun. But I might follow up with you directly with an email.
Great,
more about your
yeah,
case.
that'd be great.
But yeah, very nice work. Well, it was a comment
Yeah.
more than a question.
I think Justyna also asked one question on the decomposition of the solid parts and the parallelization, how to parallelize the solid part. Was it your question, Justyna?
Yeah, the question was if I can use different number of processors on the solid and the fluid side, but because if I reach to 3000 cores on fluid side, the solid is too small to decompose it to so many.
Right. So Philip and Professor Tuković, if you have any comments.
Maybe I'm just no is the short answer, but maybe you can trick it using a manual decomposition where you just split it on 32 cores and you tell the other 9,000 or whatever cores you have left that they have no cells. So decompose
Okay.
bar will work with that if you make a manual cell decomposition. So I've done that where I've ran it in serial where you trick it to put all the cores on one processor and then it runs in serial. So I think you can do that. Or you'll get a segmentation fault when you do that. I'm not sure. So.
Okay, yeah, thank you.
Right. So I have a question to you, Justyna, to ask that for my curiosity, what was the turbulent intensity of the experiments that you were trying to validate?
I use typical 5% in my simulation, but in the experiment, has not been provided. We haven't
all
measured
right.
that.
The other thing that in the validation, can you go back to the slide in the validation of the last final case with experiments where you compare the natural frequency? Yeah. So you match the natural frequency of the system. So what kind of behavior do you see? Is it a lock-in behavior like VIV or is it a galloping kind of behavior? I mean, how do you, in that regime, is the instantaneous frequency of the beam or is it the natural frequency of the beam? I was a bit confused.
No, I just track the displacement at the tip and extract the dominant frequency of this blue.
So it's the response
the-
frequency.
Yes, it's a response frequency.
Right, but not the natural frequency. Okay.
Yes, it's not a natural frequency of like beam in vacuum, or we call it that in experiment as well. So that's why. Yeah.
Thank you for clarifying. I'll just see if there are any questions online.
Chat.
In the chats, yeah. Can you read and answer the last comment?
The head mentioned problem related to pressure at the inverter during restarting. Yes, I've used zero gradient on the walls, and that helped. Because previously there was like extrapolated pressure, the boundary condition, and indeed there were bugs related to that when restored. But overall, like I think, I had 8 seconds of the simulation, but I don't think that's really necessary to prove that this method is working. It was just for us to see how good can we go. Definitely it is reachable to have 4 or 5 seconds within single run.
All right. So are there any?
Yeah, but restarting, I didn't have much problems when I changed to the pressure boundary condition.
Okay. Are there any further questions, Justyna? If not, please let's thank the speaker again, and we'll go for the next.
Hello, my name is Željko Tuković. I am professor at the Faculty of Mechanical Engineering, Naval Architecture, University of Zagreb, and I will today present OpenFOAM solver, which can be used to simulate fluid structure interaction in arteries. More specifically, we will use this solver to simulate fluid structure interaction in aorta, which is, as you know, the largest artery in the human body. I will first say something about motivation behind developing this solver. Then I will give most important details of finite volume solid solver implementation. I will briefly pass through the finite volume fluid solver. Then I will give most important details of finite value FSI solver implementation, and I will finalize this presentation with showing some results related to fluid structure interaction in idealized aorta model. So FSI solver, which I will present today, is planned to be used in a so-called less patient project, which is founded by Croatian Science Foundation, and in which we would like to numerically assess risk of rupture of aorta dissection. So aorta dissection is cardiovascular disease where innermost layer of the aorta is injured, allowing flow between the layers, and this can lead to serious complication, and the most important or most dangerous one is, of course, rupture. So in the project, we are focused on the type B of dissection, which affects only descending part of the dissection. So in order to predict numerically rupture, our goal is to implement so-called fluid solid growth model, which combines fluid structure interaction model and growth and remodeling simulation. Fluid structure interaction simulation is combined with growth remodeling simulations. Fluid structure interaction simulations takes into account short-term processes such as effect of hemodynamic forces of artery wall, and growth remodeling model describes long-term adaptation of the soft tissue on injury. So my task is currently to develop a FSI model. I don't know much about this growth remodeling, but we collaborate with our solid mechanics department in our faculty. They are experts for implementation of this model. They have implementation of this model in finite volume framework, and we want to implement it in finite element framework, and we want to implement it in OpenFOAM in finite volume framework. So what are main components of finite volume fluid structure interaction model, which I will describe? So it is based on a partition solution procedure, and it consists of finite volume solver for incompressible nonlinear elastic solid, finite volume solver for incompressible fluid flow on moving meshes on time-varying domains. And very important component of this solver is Arrhenius partition fluid solid coupling schemes, which should ensure stability and efficiency of the fluid structure interaction simulations. So finite volume solid solver handles linear elastic, can be used for linear elastic and hyperelastic material. It is based on total Lagrangian formulation from one side and mixed formulation, that is displacement pressure formulation for the other side. So it is used for finite volume discretization for spatial discretization, and temporal discretization can be done with various first order and second order schemes. since we have pressure and we have incompressibility condition, we also have to use re-enjoy interpolation, and I have tried to implement consistent re-enjoy interpolation, the same like we do in flow solvers. Everything is after discretization solved by a block coupled solution procedure. As a starting point for this development, I was using work by Professor Demirjic and his co-workers. So solid deformation is described by momentum equation in initial or configuration. So we are using total Lagrangian formulation. We have two variants of this momentum equation. One is used for linear elastic material, and another one is used for non-linear elastic. Actually, when you when you want to calculate non-linear elastic deformation of non-linear elastic materials, we use then both approaches. We use linear equation, which is discretized implicitly, and a non-linear part is added as an explicit correction into the source term, I would say. So incompressible linear elastic material is modeled by Hooke's law with the pressure as additional variable to enforce incompressibility, and incompressible elastic material, actually non-linear incompressible elastic material can be modeled by arbitrary constitutive equation, but here I was using only Höhn material, which is showed here. It also has this additional pressure variables to enforce incompressibility. Of course, we need incompressibility constraint, which we usually call continuity equation. So most important part is discretization of the solver, is discretization of the traction at the internal cell faces. So linear traction is discretized implicitly. So linear traction consists a normal derivative of displacement, normal derivative of normal component of displacement, tangential derivative of normal displacement, and pressure gradient term. All these terms are discretized implicitly by central differencing and by linear interpolation for pressure, except this tangential derivative of normal displacement, which is calculated using finite area calculus, and it is treated explicitly after discretization. If we choose a nonlinear material model, then it is taken into account through the nonlinear correction as a difference, which is calculated explicitly, added to the source term, as a difference between a nonlinear traction and a linear traction. Nonlinear traction is calculated explicitly using the traction calculated from the constitutive equation. After we discretize momentum equation for all cells in the mesh, we will obtain the second order partial differential equation for each cell, which has to be integrated in time. You can use, of course, first order Euler scheme, you can use backward scheme, what is usually in OpenFOAM, but I have also tried, as Philip said, a trapezoidal scheme and so-called Bathe scheme, which is combination of trapezoidal and backward scheme. Backward scheme is here to stabilize the trapezoidal scheme. So maybe one remark in the context of fluid structure interaction, it is important to have same temporal discretization scheme in both domains in order to have same acceleration at the interface from both sides. And if you do that, you don't need to do that actually, but if you do that, you will have a more stable calculation procedure and more accurate result. So second important component of this solid solver is discretization of incompressibility constraint. Two approaches I use, one for linear model, a second one for non-linear material model. For linear material model, incompressibility constraint is discretized on the initial configuration. Yeah? And on in case of non-linear model, incompressibility constraint is discretized on so-called mean configuration. This mean configuration is actually configuration between current and previous. And this is important to preserve volume after simulation, to have constant volume, so to reduce error in volume. Of course, same like in the fluid, we need this phase displacement now, not phase in velocity, but phase displacement. Yeah. And we use Riemann interpolation for that. This expression is here for case of linear model. It is calculated on initial configuration. We have this interpolated velocity part. We have interpolated pressure. We have directly calculated pressure by central differencing. And we can also add explicitly consistency correction, temporal consistency correction terms. In standard part of the Riemann interpolation, only this interpolated pressure is treated explicitly after discretization, and all other terms like this interpolated velocity and directly calculated pressure is implicit. And this is possible because we are using block solver. Yeah? So very important part of solid solver is implementation of fixed traction boundary condition. So usual approach in solids for foam is to use fixed gradient boundary condition, where this fixed gradient is calculated using iterative solution procedure. So it is, so previous normal gradient at the boundary is corrected by this difference between specified traction and traction calculated from the stress obtained using constitutive equation. After that, we need also boundary condition for pressure. Pressure is fixed, but it is interpolated from the neighboring cell center. In this study, I am using approach proposed by Professor Demirjic in his paper, where he adds traction directly to the source term of the discretized momentum equation. And because we need boundary displacement to calculate gradients, we extrapolate them actually using second order extrapolation. But I call this method TEM, traction enforcement method 1. But since we have part of this displacement, we don't need to extrapolate because we know it. We know it from Riemann interpolation. After we solve the system at the end of each iteration, we know normal component of displacement on all faces, and we know them also at the boundary. So I correct extrapolated displacement by the displacement which follows from the solution of a continuity equation. And now I still use fixed value boundary condition for pressure, but now pressure is calculated using constitutive equation. So here I show simple validation on simple case inflating on infinitely long pipe, which is relevant actually for aorta deformation, which is also dominantly deformation is also in a radial displacement. You can see difference between these two methods of enforcement traction boundary condition. So this second one, which use conservative displacement at the cell faces, is much better. Difference is even more pronounced if you look at the pressure. You see how pressure is scattered around the analytical solution. So error in the volume was very small, I would say negligible, and average number of iterations. This is large strain, I would say large deformation loading, because I have very large displacement. So this analytical solution is derived for a Neo-Hookean nonlinear incompressible equation. Yeah? Loading is done in 10 steps. Number of outer iterations for each loading steps is below 30, and there is no need for any under relaxation for pressure, for velocity. Only under relaxation is used for nonlinear traction correction, which has to be corrected since it is explicit. So here you can see comparison between different temporal discretization schemes. The same test case is used, loaded from inside by a linear step function, impulse function. So you can see here Euler schemes, which is very diffusive. You can see trapezoidal scheme, which is most accurate, and composite scheme is between trapezoidal and backward. And I would say from this that backward is satisfactory. And I will continue to use backward because it is easier for me because I have backward for flow also. Yeah? I have this trapezoidal is actually Crank-Nicolson. So maybe Crank-Nicolson can also be used. Maybe we can use a little bit larger time steps, but I think flow is asking for a lower time steps. So we will see. Fluid solver is standard based on arbitrary Lagrangian formulation. You can use in standard solver. You can use Newtonian and non-Newtonian fluids. So I would not. Pimple algorithm is used for a solution procedure and so on. So main feature of FSI solver, partition solution procedure is used, Dirichlet-Neumann decomposition, implicit coupling algorithm, iterative solution procedure, and stabilization is done by Arrhenius partition scheme. Similar solver is already implemented, but it was for compressible solid, and we need here incompressible solid. So partition solution procedure means that flow equation and solid equation are solved separately using Dirichlet-Neumann decomposition. This means that at the fluid side of the interface, we apply displacement, which is extracted from the solid side of the interface, and at the solid side of the interface, we apply traction, which is extracted from the fluid side of the interface. Implicit coupling means that equilibrium of traction velocity is enforced exactly in each iteration by using Gauss-Seidel iteration between the solvers. Added mass partition scheme is here to stabilize the solution and to allow more efficient solver. So I will start with the derivation of added mass partition scheme by deriving pressure boundary condition, which is usually used in the Dirichlet-Neumann decomposition. For the Dirichlet-Neumann decomposition, we use fixed value for velocity for displacement at the fluid side of the interface, but we also have to apply boundary condition for pressure. And this is usually zero gradient, or we can use more accurate boundary condition for pressure, which is actually fixed gradient from pressure. And this fixed gradient can be calculated using expression, which can be derived from the non-conservative differential form of the momentum equation. If we multiply it from the right-hand side by normal to the considered wall, we see that normal derivative of pressure is proportional to the acceleration, normal acceleration, but also some people, usually in the previous solver, I have omitted this term, but this term can be taken into account without problems. So this is Laplacian, but normal component of Laplacian at the boundary. I can calculate it at the cell center and extrapolate it linearly to the boundary. This is, let's say, extension of the method in respect to previous implementation. I was using only acceleration. If you use this boundary condition for fluid structure interaction, where you have densities of fluid and solid which are very close, this will cause instability, which we usually know as added mass instability. And we can stabilize this by linking pressure. So this is a condition for derivative, but we can also introduce condition for value of the pressure by linking pressure with the structure inertia. If we combine these two expressions over the normal temporal derivative of velocity, actually temporal derivative of normal velocity, we obtained this Robin boundary condition for pressure. Yeah? And this would be good for explicit calculation, but if we use implicit calculation with the iterations, we want this boundary condition, Robin boundary condition, to reduce to exact boundary condition for pressure. So this boundary condition is a little bit reformulated so that pressure is added to the right-hand side, which will cancel with this pressure when we reach converged solution. Yeah? And this boundary condition, this Robin boundary condition, will reduce to the previously defined boundary condition for fixed gradient of pressure. So problem is this virtual thickness. In case of thick compressible solid, I was calculating this virtual thickness using propagation velocity of P waves in compressible elastic material. But in case of incompressible solid, this P wave speed is infinite. So I decided to use local thickness of the solid. And this is, I think, appropriate for a shell-like structure like aorta. So this is what I do now. So but I have still problem when I have thick bodies, incompressible bodies. How to decide how to calculate these virtual thicknesses. So here you see I am comparing here performance of arid mass partition with this IQN, ILS. Two means that I'm using 2 previous time steps. And so you can see here how many outer iterations I need to reach converged solution. So with arid mass partition scheme, I need less than 4 iterations per time step, while with IQNLS I need 10. So maybe I didn't optimize it, but that is what I noticed. And case is well-known pressure propagation from through thick elastic pipe case. And finally, I would like to show some results for idealized artery case. You can see here geometry and the mesh artery. It is aorta actually. Aorta consists of arch, 3 carotids, and the descending part. Fluid domain is discretized by polyhedral mesh, and solid domain is discretized by polygonal and quadrilateral prisms. You can see here some results for FSI calculation and for CFD calculation. I would like to say something about the boundary conditions. So at the inlet of the fluid side, we specify flow rate according to hard cycle. At the outlets, we have 4 outlets. We use 3-element Wien-Kessel model, which this Wien-Kessel models are calibrated so that we get adequate distribution of flow rates, as is expected. And maybe only so boundary condition at solid side at inlets and outlets. I have implemented boundary condition, which block coupled boundary condition, which I call a radial slip, where center of the cross section is fixed, but points of the wall can move radially, so that it can expand without limitations. And here you can see velocity field in the fluid and sigma equivalent field in a solid. And I think we first calculated FSI simulation. We took mesh for one, I don't know, middle position and perform only a CFD simulation to see difference. Here you can see efficiency. So convergence data, number of FSI coupling iterations during one hard cycle. This is 9th hard cycle. And you can see that during the largest part of the cycle, number of iterations was 2. 2 was enough. So here, I don't know, maybe this works. You can see here the animation. Okay. So what is, next step. So as I said at the beginning, I want to calculate this section. So I have inner layer between, I have a false lumen, I have a true lumen, and I have wall between them. And this is problem for added mass partition scheme because it it takes into account pressure only on one side. So we can modify it by introducing other side pressure here and here, but this should be done implicitly. So I implemented something like GGI interpolation, which will connect solution of pressure at the two sides of the internal wall. Here I have some initial results related to efficiency, where blue line is the number of iterations for a single tube, which is I don't know, simpler process, and red line shows number of iterations for this more complex case with inner internal wall. So number of iterations is of course larger, but I would say it is acceptable. Yeah. So finally, I would conclude that we have implemented finite volume FSI solver, which can be used to simulate blood flow through the arteries. It is based on added mass partition coupling scheme. Initial simulations show very good efficiency and accuracy. And the next step, AMP scheme will be extended to work with internal blood vessels, which is already done, but we need some optimization, I suppose. Thank you very much for your attention.
Thank you for the nice talk. So,
Thank you.
you're open to questions. Are there any questions from the audience? If not, I'll just check if there are any questions on.
I think no.
I have one question. Okay. The slide before, when you talk about pressure.
Which one? This one?
Yeah. So you do something like an average pressure. And then
So I take pressure. So if I am in this phase, I take pressure at the nearest phase at the opposite side.
Okay. And then average over it?
This is so this comes from, for example, this comes from this equation. So P equals mass multiplied by accelerations. But this is if P on the other side is 0. But if P on the other side is some finite value, I need P at the opposite side. So, and difference is important, not absolute value. Difference is important. Yeah.
Any other question? So I have a question to ask you. So with this new added mass implementation, what is the minimum mass ratio you can reach accurately? So first of all, what is
What do you mean by mass ratio?
I mean
Mass ratio,
mass
density ratio. So my density of fluid can be of a solid can be smaller than density of solid of fluid.
less than 1.
Yes.
That's
Yeah.
impressive.
Yeah. Thanks.
Thank you. If there are no questions, let's thank the speaker again, and we'll move on.
Thank you.
I invite Mr. Patrick Höhn to give his talk on application of solids for foam to the damping of big string vibration.
Thank you for the nice introduction. Today I tried to, as I said, study the damping using solids for foam and somehow summarize what I have presented in the last 2 years ago and 3 years ago. I did not make it to run the simulations in solids for foam, so I structured the talk a little bit different today. At first, still I will give an introduction, why it's important, what is causing drill string vibrations. We'll talk about results which I have got in this year during an experimental study. And then I will talk about how I want to do the simulations, what my next steps are, and finish with some conclusions and outlook on future. First of all, I'm from the drilling industry, or petroleum industry, which might not be so commonly known here. So I give a bit more general introduction. Drilling is important because for oil, gas, geothermal energy, we need to drill pretty much below ground. And especially when we want to do geothermal energy, it's pretty much important to cut drilling costs because there we have the problem that the return of invest is lower, the risks of actually being successful is quite a bit higher compared to the petroleum field. And many of those challenges, when you are not successful, is, for example, when your drill pipe is stuck or you have other mechanical problems, you cannot drill and the costs keep running. So those kind of problems related to non-productive time, that's often related to drill string vibrations and also a non-optimal cutting transport. As I don't have access to an oil field, I'm doing it in the lab and in simulations. Now, here you can see how you can imagine a drill string in a well. We actually also have horizontal sections, which is maybe not common for the usual people. And then we have a cutting bed that are all blocks which are during drilling. And just to give you a maybe 20 meters in diameter, but it can be a few kilometers long. So it's a very slender structure which can oscillate any direction you want, torsional, axial, and lateral. And what I'm mostly looking at is oscillations and damping due to drilling fluid flow and cutting beds, because that is what I wanted to focus in my PhD on. So here I show you a bit how my setup looks like, both in simulations and also in the experimental setup. Despite in the simulations I have some limitations which I don't have in the experimental setup. First of all, I have also a pipe which is fixed at one end, which where we have a motor so it can rotate, and from the other end we have the flow that also carries particles. In some of the experiments and in the late stage should be also in the simulations. And then we induce some vibrations at the free end and study then how the oscillations are damping out. Now, my experimental setup, that flow loop is located in Clausthal, and there I won't go through all the details here now, but just to give a brief overview, we have here some hydrocyclone to take out the particles, which we can feed back via a screw conveyor. In my horizontal experimental section, here I have my inner pipe which I can oscillate using permanent magnets in the pipe with an electromagnet, and the IMU where I have accelerometers, magnetometers, and that is mostly the measurement data I use, what I present here. In addition, I also have some optical measurements. I have 2 GoPros installed in order to also have an absolute measurement system, but that is nothing which I will talk about here. And then the measurements from the IMU are sent out via Bluetooth and recorded. And that's actually also the data which I will show you in a minute. Here you see how such accelerometer measurements can look like. I should mention we take the measurements with a frequency of 200 Hertz. That's why it's also a pretty much solid block. And basically what we are just trying to finally do is to fit here an exponential function and take that exponent as my so-called damping coefficient, which in this particular case was 0.5157. And basically that is also what I want to compare later on in my simulations, or with my simulations. So when it comes for the simulations, as in previous talks, I'm using solids for foam for the FSI part. And what I talked today about is just FSI. Initially, I also wanted to factor in particles, which is something for the future. And there I try to replicate now in what I talk about today, the experimental also do some pure solid simulations where I want to just say, okay, if I have oscillations in air, that is a pure solid case, just to also have a clear comparison between the air case and the cases with more dense fluids. And then, as I said, for the future, I would like to also have my particles, but not for what I'm talking about today. So this is here the solid mesh which I created, with which I also already, which I think should also work. I already had solid simulations which were running, so that I'm rather confident. For the boundary conditions, maybe I can talk a bit more about those. For the pipe, I just split the domain in half because it's a symmetric case, just to save computing time and also memory. Here's the inlet. This is where I have fixed my inner pipe, so there no movement is allowed. The outer wall is where we have the interface to the fluid. The inner wall is just because it's not a solid, but it is actually a pipe, like a drill string, and also in my experiment. So that is that patch. And here at the inside, what I call the outlet, that patch is pretty important for me because this is where I introduce my force in order to initiate the oscillations and then stop the force at a certain point in time and then see how it dampens out. For the fluid mesh, it's actually pretty similar to, as well, to what was presented, I think, 2 talks earlier, where we also just have more or less a fluid domain where we have the pipe embedded, and at the end we have a free space where the fluid flow should develop. And here actually I'm using pretty much extrapolated pressure. Maybe that's one of my problems of the convergence issues which I have, as I done today in that other talk. So maybe already I took something from there. And here I'm using a constant flow rate, which enters here the inlet as that, and that's the outlet. And again, I'm using there a symmetry in order to speed up things. Then, yeah, as I already mentioned, I have a fixed flow rate. That is where I have here a fixed value for my inlet in the speed. And I think the other conditions are pretty much standard. Now, if we combine it, I also just wanted to show it. As I said, just thinking about the other talk, I see exactly the same geometry. So basically, we have the flow coming from here, and then we should see how it dampens out actually in that direction. For the properties, in my experiments, I used 4 different fluids. I used water, and I added 3 different sugar concentrations. I added in the flow loop. The flow loop has round about a volume of 1.5 cubic meters of water. So in there I was doing it with concentrations where I added 100 kilograms of sugar, 200 kilograms of sugar, and 800 kilograms of sugar. Yet I realized that I did a mistake in my calculations. I wanted to reach a solid fraction of 60%, which would have meant I had to add 1200 kilograms of sugar instead of the 800. So I ended up with 40% solid fraction. But yeah, that's what happens in experiments. You do mistakes. And then I ran it at different flow speeds. And yeah, here's the viscosity corresponding to the densities for the different fluids. And for the inner pipe, I'm using the carbon fiber pipe. That is also where the Rho and the Young's modulus come from. And as I'm still a bit playing with learning how to use solids for foam, I'm also using different solid models just to also compare. And also for the fluid models, I'm using two, the ico-fluid and the piezo-fluid. But what was important for me in my whole study, I want Newtonian flow. I don't want to take also the challenge of adding there in addition non-Newtonian fluids. Despite, I would say, when it comes to drilling, there you actually rather have non-Newtonian fluids. But I didn't want to overcomplicate it for myself. Then that already brings me more or less closer to my end. I set up now simulation cases with pure solid simulations with FSI, and I want to compare them then with my experimental data, where I have quite a few different scenarios, as I already showed also in the slide before. They somehow replicate also my simulation settings. And once that is done, actually I would say for me the more exciting work will start again, because then I want to restart my efforts to integrate the particle transport based on CFDM coupled lights into solids for foam as a new fluid model, and in that way also achieve what I think XDM calls also a six-way coupling, so that the particles affect also the solid, it bounces back, and also we have the FSI as usual. So in that way, it's a bit similar what was presented by the colleagues from Luxembourg. And what is there still different for me in my current code, it's not perfect as usual. One limitation which I still have, right now I don't have any interpolation in terms of time step when it comes there for the movement of the solid mesh compared to the particle movement. So right now I need to couple every CFD time step to every DEM time step, which certainly is not the way to do it. But that's something which I would also work when I'm working on the integration again. And one thing which I was already promoting also in the Woover app quite a bit, I should also mention it here. All my work which I was previously doing was based on the public version of CFDM coupling and lights. But now I will move over to the particulate flow modeling fork, PFM fork, because that's actually developed and also integrating other community contributions. So hopefully I will be also able to upstream my code there. And then finally do the simulations of the influence of particles on the damping of my inner pipe, or later on for drill string vibrations. With that, I want to come to the conclusion. What have I achieved so far? I have created my validation data set, so at least the experimental part is done. I talked about how I want to do simulations to make use of my validation data. And then I talked about how I want to go forward with my software development, combining FSI and particle transport, and then also reach the simulation of the full effect, which I was talking about now for 3 years. So with that, I would like to thank my co-authors. I would like to thank the Federal Ministry for Economic Affairs and Climate Action for funding my work, and the HLRN, the Northern German Supercomputing Alliance, for providing me also computational power, and of course you for attending this talk.
So, are there any questions for the speaker?
speaker?
Just a tiny one on the experiment. So you added sugar as a part of your part? I mean, isn't that getting this also?
No, I mean, my goal was to have a more dense fluid, not only density, but to increase the viscosity. That was my main goal. Initially, I wanted to use oil, but HSI regulations can be really difficult. So I ended up with buying a tiny bit of sugar.
Any other questions?
I did not fully understand why you use 6-way coupling. So 4-way coupling would be like interaction between particles and feedback to the flow.
Yeah.
Flow particle flow
Yeah.
interaction. So 6-way coupling would be interactions also to the wall.
And to the and to the wall, exactly.
Okay. And then so how big are your particles? And they have a lot of mass. So is there like a strong impact of particles on the structures?
I would expect if they are just immersed in the fluid, probably not. But I would expect a larger impact if you have a particle bed, which basically was in all my experiments. If I had particles in the experiments, I had a particle bed because I could not run the flow loop as fast as I wanted to really have them immersed in the flow. And that's also, I would say, the most crucial part when you look at the application in the drilling industry.
All right. I see that there are no questions online. So if there are no more questions, then please let's thank our last speaker. And we conclude the session for the day and enjoy the banquet. Thank you all.